Alrighty, so, I guess I got to turn on here. After a long week of review and whatnot, we still have Mitch. I think I still need you to write the momentum test. Am I right? Okay, so we'll have to make arrangements to do that. Those of you that are waiting on news, I'll get some marking done tonight. But it's time to start the next topic here. There's actually 2 units that we're going to have to work pretty hard to get through here. So let's begin with circular motion. So if you could, pull. I've been sort of, talking gibberish here, kind of really just filling space, hoping that you would realize that. Yeah, 5 seconds. Yeah, okay. All right, so as I was saying, let's begin circular motion. No, I'm hoping to do one more after this, too. Far more than we cover, Nate. Oh, yeah. Like, I don't even come close. I should be going at about 2.5 times the speed that I'm going. Great question. I have no answer for you. No, but be aware that if you're taking university physics, when I spend a week or a week and a half, that's one lecture. Seriously. Like projectiles, projectiles would be 1 day, maybe a lab. Dynamics, maybe 2 days, maybe. Like way faster. Usually 3 times a week. Nate, how many people in the room have been to university? It is. Usually it's 3 times a week or twice a week for a longer period of time. Anyway, so if I could begin. So here's the outcomes for circular motion. Explain qualitatively why an object moving at constant speed in a circle is accelerating toward the center of the circle. We're going to cover that today. Discuss the centrifugal effects with respect to Newton's laws. We're going to cover that also today. Draw free body diagrams of an object moving in circular motion, in uniform circular motion. Let's sort of talk about that today. Experiment to determine the mathematical relationship between period and frequency and one or more of the following: centripetal force, mass, and radius. We'll be doing that tomorrow and Wednesday in class. It'd be really nice if we could do it all in 1 day, but for some reason, a 1-day lab has turned into 2 days in the last 5 years. We will derive an equation for the constant speed and acceleration of an object moving in a circle. I will do that for you based on our results from the lab, and that's the equations we're going to get. And then we will solve problems for an object moving with constant speed in a circle using those formulas there. And the problem types are horizontal motion, vertical motion, and banked and unbanked curves. So it's actually fairly short. The formulas themselves get a little bit crazy. Those are the ones that are listed in the curriculum, and I'll give you slightly different ones as well. Okay, so that's where we're going. I think this is the one that I start with. I think it. Wear a helmet. I think I've done that before. That's not good. Okay, normally this would be done via clicker, but given the distance and the lack of clicker receiver in here, we'll have to do it in a paper format. So this is just introductory stuff. There's 6 questions. How about you guys take 6 minutes to do those, and then we'll go through them. Go. You are spinning a bucket attached to a string in a circle above your head. What kind of force holds the stopper in a circular path? Is it centripetal, centrifugal, or maybe C, you don't know? How many people said C? No one said C? Yeah, the correct answer is B, centripetal. Centripetal. Oh, I meant A. A. Centripetal force holds the stopper in a circular path. In a washing machine during the spin, maybe, are you guys familiar with the washing machine lives in your basement? Maybe, some of you? Little joke there. Are you familiar with the washing machine in your house, Nate? Do you know where it is? Okay. In a washing machine during the spin cycle, the force is on the what causing the water to be separated from the clothes? Is it on the water, the clothes, or you don't know? Why do you say clothes? But I thought that the force... Okay, yeah, no, I can't say that just yet. Okay, well, you're right. It's on the clothes. A tube is placed upon the table and shaped into a three-quarter circle. A golf ball is pushed into the tube at one end at high speed. The ball rolls through the tube and exits to the opposite end. Describe the path of the golf ball as it exits the tubes. Is it A, is it C, or is it B? It's B. It comes straight out. Straight out. Just like at the mini golf, right? Mr. Bennett is spinning a rubber stopper at a constant rate of 3 revolutions per second. The rubber stopper is accelerating. The answer is? Why, Sam? Changing direction. Changing direction. By everlasting admiration. At least until the end of the period. Mr. Bennett is still spinning the rubber stopper. What direction is the force in the stopper? Cole? Not C. The force is in. The force is in. I will explain once we go through the reading. Force is in. Sorry, Cole. When you're driving your car and you make a left turn, friction between the tires and the road causes the car to move to the left. You're driving your car, you turn the wheel. Is it friction that causes your car to move to the left? And the answer is yes. Your car tries to go in a straight line, but friction pushes it in, right? Which is why when there's no friction, when it's icy, your car will continue to go straight. Okay, so you guys have this handout, right? I think. This will explain everything here. Okay, so if you whirl a string, let me get it here. Where did I put them away? Put it over here. If you whirl a tin can on the end of a string, you'll find that you must keep pulling on the string. You pull inward on the string. Inward on the string. Where's my... Oh, I can't do it. You pull inward on the string to keep the can revolving over your head in a circular path. A force of some kind is required for any kind of circular motion. Any force that causes an object to follow a circular path is called a centripetal force. Centripetal means center-seeking or toward the center. I think it's probably Latin. Okay, I don't have a tin can, but I have a rubber stopper, and I have to be careful here for a couple of reasons. Don't let me hit I should probably bring a helmet for this demonstration. Okay, so what direction am I applying the force? Inward, right? On a string, you can only pull. You can't push, can you? So how could the force be? Outward. The only direction that the force can be is toward the center, right? Now, you've all been on these type of feelings. You feel like you're going to the outside, but is there a force on you? No. In fact, that force is inertia. Inertia is trying to get you to go straight, but the force is in towards the center, and that causes you to move any circular path. Hello, Mr. Chatter. Can I do for you? Oh, okay. Okay, sounds good. So without it, the motion of the occupants would be along a straight line. They would not revolve. So centripetal force is the word. Centripetal. Centripetal force is not a new kind of force. It is simply the name given to any force that is directed at right angles to the path of a maneuvering object and tends to produce circular motion. So that's a better definition for centripetal. It is any force that is directed at right angles to the path of a moving object, right angles, and tends to produce circular motion. Gravitational and electrical forces act across empty space as centripetal forces. What holds the moon in place in orbit? Gravity. Is the motion circular? It is. If there was no inward force, the moon would continue in a straight line forever. Gravitational force directed toward the center of the Earth holds the moon in an almost circular orbit about the Earth. Electrons that revolve around the nucleus are held by an electrical force that is directed toward the central nucleus. So again, the word is centripetal. Centripetal force plays the main role in the operation of a centrifuge. A similar example is a spinning tub in an automatic washing machine. In its spin cycle, the tub rotates at high speed. The tub's inner wall exerts a centripetal force on the wet clothes. It keeps the clothes going in a circle, which are forced in a circular path. The tub exerts great force on the clothes, but the holes in the tub prevent the tub from exerting the same force on the water. The water therefore escapes. It's important to note that a force acts on the clothes, not the water. That's the answer to that question. Another common example of this that you have in your kitchen maybe is a salad spinner, right? It's the lettuce that is forced into a circular path, and the water escapes. Why does the water escape? No force causes the water to fly out. The water will do that anyway, as it tends to move by inertia in a straight line path, unless acted upon by a centripetal or any other force. So interestingly enough, the clothes are forced away from the water and not the other way around. When an automobile rounds a corner, the sideways frictional force between the tires and the road provides the centripetal force that holds the car in a curved path. If the force of friction is not great enough, if it's icy or you don't have your winter tires on, the car fails to make the curve and the tires slide sideways and the car will skid. So it is a centripetal force here that is provided by friction. It's every time after this, when you're driving today and you make a turn, whether it be left or right, I just want you to think about, you're making the turn and it's actually friction that's pushing you into that circular path. It's kind of a weird thinking as you're making that turn. Please be aware of your surroundings when you do it. Okay, so centripetal and centrifugal. Most people know the word centrifugal force. So let's talk about it. In the preceding example, circular motion was described as caused by a center-directed force. Sometimes an outward force is attributed to circular motion. This outward force is called centrifugal. Centrifugal means center fleeing or away from the center. Centripetal is in, centrifugal is outward. But I have to give you more about centrifugal. In the case of the whirling can, it's a common misconception to state that a centrifugal force pulls outward on the can. Not true. If the string holding the whirling can breaks, it's commonly stated that a centrifugal force pulls the can from a circular path. That would be wrong, false, not true. As I'm whirling the rubber stopper around above my head, I pull inward on the string. Does the rubber stopper pull outward on the string? Equal and opposite, right? Is there tension in the string? There is, right? So the force is not on the rubber stopper. The centrifugal force is actually on the string. It's commonly stated that centrifugal force pulls the can from the circular path. Not true. But the fact is that when the string breaks, the can goes off on a tangent straight line path because no force acts on it. We'll illustrate this further with another example. I'll do it in here. Nate, I'm coming at you. I'm going to let go. It's going to go flying towards Nate. Where do I have to let go so that it goes? Sorry, did I say Nate? Nick. Where do I have to let go so that it goes to him? Do I let go when it's at the front like this? Right there, right? Whoops. Good thing Mr. Johnny didn't walk in then, right? It would have been hilarious. I didn't do it just right. I thought I did it at the right time, but I think I was thinking about I was wanting to do it there, but I was looking over there and yeah. Concussion. Yeah, I shouldn't be doing that. Okay. Suppose you are the passenger of a car that suddenly stops short or stops quickly. You pitch forward against the dashboard. When this happens, you don't say that something forced you forward. If you're driving in the school bus and the bus driver hammers on the brakes, everyone goes like this, right? Did anything push you forward? No, it's inertia. You know that you pitch forward because of the absence of a force, which a seatbelt would have provided. Similarly, if you were in a car that rounds a sharp corner to the left, you tend to pitch outward to the right, not because of some outward or centrifugal force, but because there is no centripetal force holding you in a circular motion. The idea that a centrifugal force bangs you against the car door is a misconception. It is not true. Okay? If I'm driving the big bus and we're going forward, right, and I crank the wheel left, we all go. Do you really go to the right? You just go inside. In the bus, you go to the right, but in reality, what are you trying to do? Continue going straight, right? Continuing to go straight. So when you swing a tin can on a circular path, there is no force pulling the can outward. Only the pull by the string acts on the can and pulls the can inward. The outward force is on the string, not the can. Put a little star there. The outward force is on the string, not on the can. Okay, now to further blow your mind. Imagine that there is a ladybug inside the whirling can. The can presses against the bug's feet and provides the centripetal force that holds it in a circular path. So the can will push on the ladybug and will hold it in that circular motion. In reality, it's what happens to the clothes in the washing machine. Same thing. The ladybug in turn presses against the floor of the can, but neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet. From our outside stationary frame of reference, we see there is no centrifugal force exerted on the ladybug, just as there was no centrifugal force exerted on the person who lurched against the car door. The centrifugal force effect is attributed not to any real force, but to inertia, the tendency of the moving bug to follow a straight line path. Try telling that to the ladybug. If you've been on the, what's that thing at the fair called? I always forget it. Oh, so no, it goes sideways, where you stand up, right? What's that called? G-force? You walk in, it's like a flat circle thing, right? There's like little compartments, little handles, and then there's this little dinky chain that, what's the point of that? Absolutely nothing. That I would like to see, Nate. You dancing in the, what's it called? G-force? It spins you like this, right? Does that chain do anything? No. I don't really, they might as well not even. It's literally, they might as well have a string like this, because that's like, it's not doing nothing, right? Yeah. I was in Calgary once at an amusement park, and they had a very similar ride, and I noticed that they actually didn't even have, all the other rides have, like seat belts for the roller coaster stuff. This one didn't, and it was the same thing. It's just circular motion, and all it does, it just keeps you pressed up. There's no way, you cannot, in that G-force thing, you can't step out, right? Nate apparently can dance, but I don't know. Yeah? That would be dangerous. Yeah. Okay, so it's called the centrifugal force effect, and it's really just inertia. Okay, now centrifugal force in a rotating reference frame. You guys have this page as well? I think it's the last little bit, right? Our view of nature is very much influenced by a frame of reference from which we view it. When we sit on the seat of a fast-moving train, we have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground outside. We've just seen that in a non-rotating reference frame, in other words, you outside on the ground looking at the people in the G-force, the force that holds an object in circular motion is a centripetal force. But for the ladybug, the bottom of the can exerts a force on its feet. No other force was acting on the ladybug. So where does that force come from? It's the inertia. Nature seen from the reference frame of the rotating system is different. In the rotating frame, in addition to the force of the can on the ladybug's feet, there is a centrifugal force that is exerted on the ladybug. If you're inside the rotating reference frame, you feel the force, you can describe the force, you see it. Centrifugal force in a rotating reference frame is a force in its own right as real as the pull of gravity. However, there is a fundamental difference. Gravitational force is an interaction between one mass and another. The gravity that we experience is our interaction with the Earth. But centrifugal force in the rotating reference frame is not part of an interaction. It is like gravity, but with nothing pulling. Nothing produces it. It's inertia. It is the result of rotation. For this reason, physicists rank it as a fictitious force and not a real force like gravity, electromagnetism, and the nuclear forces. Nevertheless, to observers who are in a rotating system, centrifugal force seems to be and is interpreted to be a very real force. Just as from the surface of the earth we find gravity ever present, so within a rotating system, centrifugal force is ever present. Anyone seen the TV series The 100? Okay, and they start off, you guys like that? Okay. They start off the very first season, right? They're in a ship, right? Called the Ark, I think, right? And isn't it a big giant circle that does what? It spins, right? And why does it spin? To create gravity. Okay, so they have created that artificial gravity by making it spin. Now, when you watch the show, I actually mocked the first season, the first episode, because they're walking around because it's happening on a soundstage, right? But it would really be a whole lot at the rate that it was spinning. You wouldn't get that kind of gravity. You'd just barely be hanging on. And of course, everyone would actually be walking. Like if it's rotating like this, right? Yeah, you'd be sort of walking on the walls, right? Everything would have to be. It would seem to be the ground to you, right? But you'd be walking. If you walk down a long hallway, you'd have to actually walk up it, right? Like this. No, I like doing that. Picking the holes and stuff like that. Yeah. Maybe, yeah. Maybe. I don't know. Okay, I got a couple questions for you here, and then I'm going to quit talking. Challenging questions. A heavy iron ball is attached by a spring to a rotating platform as shown in the sketch. It's a merry-go-round. Yeah. Two observers, one in the rotating frame, that's the boy, and one on the ground, this girl, at rest, observe its motion. Which observer sees the ball being pulled outward, stretching the spring? Which one sees the spring pulling the ball in a circle? Which observer sees the ball being pulled outward, stretching the spring? Is it the boy or the girl? Yes, he's spinning with it. He sees that centrifugal force. You're right. Which observer sees the ball being pulled outward, stretching the string? It is the boy. Which sees the spring pulling the ball in a circle? That's the girl. This is the second answer. Okay, because she's outside, she sees the ball going in a circle. Does he see the ball going in a circle? He does, but only because he can see the outside here. If we built walls in this rotating reference frame and he had nothing to gauge, and if he was born in that rotating reference frame, what would he see? He was born, he's never known any world different than this rotating reference frame. What would he see? He would just see this ball out here and it would just be sitting there. Just like you and I are all sitting here on a rotating reference frame. Do you see the stapler rotating? No. It's on the earth, it's moving, right? I'm sitting here moving. We don't see that motion because we have nothing to sort of compare it to. No frame of reference. Okay, last question. The spring in the sketch is observed to stretch 10 centimeters when the ball is midway between the rotational axis and the outer edge of the circular platform. So in other words, they start the ball right here, the merry-go-round starts going, and it's stretched 10 centimeters. If the spring support is moved so that the ball is directly over the edge, will the spring be stretched more than, less than, or the same 10 centimeters? So instead of this post being in the center, the post is now moved out to here somewhere. The ball is now on the outside, right? Will the spring be stretched more than, less than, or the same 10 centimeters? Why more, Mitch? This feels right. When you've been on a merry-go-round, where do you move the fastest? On the outside? Let's say the whole thing takes 2 seconds to go all the way around, right? If I take 2 seconds to go all the way around there, I've traveled the circumference of it, right? If I'm standing in here, I do the same 2 seconds, but a much smaller distance, which means I'm going slower. I'll have to be going faster on the outside, right? And you feel that when you're on a merry-go-round, if you're way on the outside, right? If you're starting to feel sick, where's the best place to go? Towards the center. You're moving less, right? So it will be stretched, you're right, more than. That is all I have.